Yeah.
Yes, it is being recorded. Okay, very good. So now just one more second here so I can introduce the speaker. Yeah, give me 1 second here. All right, so good morning, everyone. We are going to get started here. So today we have Professor David Mays giving us a seminar, who is one of our own. He's a professor at Civil Engineering Department here at CU Denver. And yeah, he's gonna talk, the title of his talk is Out of Cow Comes Engineered Injection and Extraction. And well, he will tell us what that is about, of course. And yeah, so before we get started, as I said, I wanted to mention that Professor Mays is a professor here. He's a local professor. And yeah, he has degrees from Penn State, University of Pennsylvania, as well as UC Berkeley. Yeah, and he's been with us, I believe, from '96, right, David? Or 2006,
here in
sorry.
2005.
2005, sorry. I meant to say 2006, but I missed it by 1 year. All right, very good. Yeah, so without further ado, I will give you the stage to you, David, and please, so are you okay with questions during the seminar?
Yes, that would be fine. And I have a question for you. How long would you like me to speak before we wrap up?
Yeah, so we should get finished by maybe 11:50, you know, maybe 50 minutes of talk and then 10 minutes of question. That's more or less what we have in mind.
Yep, that's
And
what I had in mind.
so Maxi is going to be reading the questions on the chat if people choose to write the questions rather than, say the questions, okay?
I might interrupt you, so.
Okay, thank you.
Let's go ahead. The stage is all yours, Dave. Thank you so much.
All right. Well, thank you, Professor Mencia David, for a nice introduction, and good morning to all. There's some familiar faces out here and some new folks. So I'd like to welcome everybody to today's seminar, which on the one hand is very far out, radical stuff, because we don't always talk about chaos theory in engineering. But on the other hand, it's very traditional hydraulic engineering and design, as you'll see as we go through the talk. So I've been very happy about this component of my work here at CU Denver since I started, nearly 18 years ago. And I am happy to take questions as we go. I guess anybody can ask. I probably won't be monitoring the chat, but I think Maxi's going to do that. So let me go ahead and click on share screen, and I will pick out my slideshow, and that should work. All right, can somebody raise their hand if they can see my PowerPoint, please?
We can see it very clearly, David.
All right, very good. So the title of the talk is Out of Chaos Comes Engineered Injection and Extraction. I'll explain each of these terms as we go. Here's a quick outline. I'll start off with some acknowledgements so I don't run out of time at the end. Then the story will begin in Philadelphia, where I was a college student. My last year in college, and that'll kind of get us into the idea of chaos theory. The simple idea that you can have totally unpredictable things coming out of completely predictable equations. And then we'll do an example where I'm going to ask for some participation by anybody who has a calculator, and I'll remind you that your smartphone has a calculator on it in case you didn't bring yours. I just want everybody to have the experience of generating a chaotic time series. Because it's so simple, we can do it right here. Then the story moves to Denver, Colorado, where we pick it up in my first year being a professor and focusing on groundwater remediation. The second example is a hands-on example. And if you are physically sitting in North Classroom building, I would be delighted if somebody wants to come by and do the physical demonstration here. It's more fun when we have a person to demonstrate. If not, I'll be more than happy to do that myself. Professor Markshausen possibly might be interested. But if you're interested, it's North Classroom 2014, as in 7 years ago. That's my office number. Just come by, knock on the door, and I'll let you in. Then we'll move on to a discussion of, engineered injection and extraction. This is an approach that I've developed with collaborators at the University of Colorado up in Boulder. And we've done analytical work, numerical work, laboratory work. And then the next step is to try this in the field. So we're currently developing relationships with groundwater consulting firms. And I'll wrap up with a few conclusions. So here's the map. We start off with Pennsylvania, we go to Colorado, and we end up with some really cool experiments. I never thought I'd be dealing with high-powered lasers when I started in civil engineering. So here we go. I'd like to start by acknowledging the land where I am currently sitting is the traditional territory of Arapaho, Cheyenne, and Ute people. Here's a map I downloaded recently that shows that there's a great deal of overlap with all of these folks. And I'm happy to report that anybody who's a member of these tribes or any of the other traditional tribes of Colorado, because there are about 40 others, is eligible for in-state tuition. I'd also like to acknowledge some people who made all this work possible. The first and most important is my collaborator, Rosanna Newpower. Rosanna is a fantastic collaborator in every possible way. She challenges me in my writing, in my thinking, in my teaching. She's been a role model and a mentor, and I can't say how much I appreciate it. And she has been involved with every step of the research that I'm presenting on engineered injection and extraction. So I want to say thanks to Rosanna. I also want to acknowledge a person who is not involved in any of the research I'm presenting here, but Professor Garrison Sposito, one of my PhD committee members at the University of California, Berkeley. He published a paper in 2006 that opened up a possibility for me I hadn't considered, which was how to use ideas from chaos to improve the cleanup of contaminated groundwater. That paper opened up what turned out to be an interesting chapter here in my career. I'd like to acknowledge the National Science Foundation for providing support through their hydrologic sciences program. And maybe this is not so much of an acknowledgement, but more of an apology to Friedrich Nietzsche, who said, "Out of chaos comes order." So I stole the title of my seminar from him, essentially. But this is a recurring theme in the people who study chaos. And it gave me hope as a college student that maybe some of the unpredictable things in the world. I graduated from high school in 1991. The Soviet Union fell apart very quickly just after that. Nobody really predicted that. How does something that unpredictable happen? We have a lot of unpredictable turns in the stock market. There are so many people who focus on that. How come nobody can predict that? And we have all had the experience of weather forecasts a week from now being completely wrong. How is that possible? It gave me hope that maybe underlying some of the craziness in the world, there is a structure and an order. And if we can figure that out, it's going to allow us to do great engineering. So it's been fun to play with that idea here at work. So the story starts 1994, 1995 in Philadelphia, Pennsylvania, where I was a senior at the University of Pennsylvania. Here's the quad. I lived in this old Gothic building for 4 years while I earned my first degree in civil engineering. In my final year, I took a graduate course in physics. I took it pass-fail, and I'm very proud to say I passed. The topic of that course was called classical mechanics. So it was not quantum mechanics, and it was not relativity. It was classical mechanics, but that included the possibility of this thing called chaos. So as part of that class, I read this book by James Gleick. This book was really mind-opening for me, and it got me thinking about chaos. So let me define a little bit what that means. There's no standard definition for chaos that everyone agrees on. But the number one thing people probably talk about is this thing called sensitive dependence on initial conditions. You may have heard about the butterfly effect. This is the idea that a butterfly flapping its wings here in Denver can trigger a hurricane in the Philippines, because maybe that little parcel of air is going to move, and maybe it's going to trigger one thing that leads to another. And before long, small inputs can turn into big outputs. As opposed to what we think of in traditional systems, if you have a small change in the input, you get a small change in the output. So here's two ways to illustrate this. This is in the format of a fluid flow where we have what we'll define later as a periodic point. So if I have one particle here and another particle here, particle 1 and particle 2, particle 1 will travel off to the top, particle 2 will travel off down to the bottom, because they just happen to be on opposite sides of the structure, which we'll call a manifold later, but that acts like a ridge. So if you're on one side of the ridge or the other, you'll go one way or the other. And that's exactly the same concept that anyone will be familiar with if they've been skiing. So here in Colorado, this metaphor works for some. Not everybody skis, but some people do. If you're on a ridge, depending on which way you turn, one way or the other, you could end up in a radically different location. So it's important to communicate with your ski buddy before you turn left or right off the ridge, because that's a place where a small change can lead to a big outcome. And it turns out this property doesn't require anything exotic or even random. So what I'd like to do here is run through an example. And we'll start off with a beautiful picture of Dream Lake up in Rocky Mountain National Park. What a beautiful place. What we're going to think about in this lake is trout. So here's a picture of Brooke Duncan catching a trout in one of these high alpine lakes. So what I want you to think about is the trout population varies from 0 up to some maximum population. Let's say there's a maximum population. The lake can't support more than that. And then we're going to define a normalized population variable of P over P max. So now X is going to vary from 0 to 1. So 1 would mean we're at maximum population, and 0 means we're at 0. Okay, so far so good. That is a pretty simple population model. We're going to predict the population next year. So sorry, that should be subscript n plus 1. So population in year n plus 1 next year is going to be a fertility factor R times the population this year times 1 minus the population this year. This one accounts for growth. This part accounts for overpopulation. If you get too many people, things will blow up. And then that fertility factor varies from 0 up to 4. So what I'd like is to try this with R equals 2 and then R equals 3.7. All right, now to do that, I'm going to call for some volunteers. So I'm going to stop sharing for a second. Then I'm going to share a different screen when we get there. So I'm looking for a volunteer who has a calculator and is willing to punch in some numbers for the benefit of engineering education. I'm looking for volunteers.
I mean, I could do it, but I would rather have a student doing that. Maybe.
I guarantee it's going to be really easy compared to any other engineering math you've seen. You could have done this when you were in 5th grade.
Maybe my baby Noah is volunteering. He said good morning.
It looks like Professor Markshausen is willing to volunteer. All right.
I would do it.
All right. So I'm going to switch over to a worksheet. I'm going to share that. Okay. So we've got different time steps here. Well, first of all, could somebody raise their hand when they can see my screen with a Excel spreadsheet?
Good.
Great. So we need to start off with some population, and then we'll calculate 1 minus that population, and then we'll calculate the next population. Real easy. So Dr. Markshausen, where do you want to start?
Well, let's start in the first cell. The n equals 0.
Okay. Well, now if you start at 0, we're going to get back 0.
Oh, right.
If you got to have some fish to begin.
All right. So we'll start at 1, right?
Okay. So let's start at 1. See what happens. Okay. So what's 1 minus the guess you just punched in?
Well, that'd be 0. I got it. I thought you meant on the line. I wanted to fill out the chart. I got it. So we're actually starting at 0. So the population. Let me change my population start initial of 10. So 1 minus 10 is
okay. So remember, X has to go from 0 to 1.
Oh, 0 to 1. So all right, let's start at 1 then.
Okay. So if we do, well, let's just try it. If we do 1 here, so 1 minus that is going to be
0.
0. Okay, and then the equation is R, which is 2. So 2 times 1 times 0 equals what?
2. Say that again one more time.
So according to the equation, so let me write this down here. So it's x n plus 1 equals R times xn times 1 minus xn. And let me go in here and put the subscripts.
All right.
So there's a subscript to make that easier to read. Here's a subscript to make that easier to read. And here's a subscript to make this easier to read. All right, that's my logistic map right there.
2 times xn. So 2 times 1 minus xn would be 0, right?
Yeah, that's going to be 0. Yeah. So if you
Right.
have either 0 or 1, your population goes to 0 and then you're done.
Ah,
That is a perfectly legitimate input, but I wonder if we could try some other starting point besides 1.
so if we get if our bounds are 0 to 1, we'd have to start at, let's say, 0.5, right? Can we start
Okay,
in the
let's
middle?
try 0.5. All right. So if I go with 0.5 here, 1 minus 0.5 is
1 minus negative 1 minus 0.5 is 0.5.
0.5. And then what is the result of 2 times 0.5 times 0.5?
2 times 0.5 plus 0.5 is going to be 1.5.
Oh, well, it's going to be 2 times 0.5 and then times another 0.5.
Times another 0.5.
Right.
Did I do that right? 2 times 0.5 times 0.5
It's
is
going to be 0.5.
0.5.
It's
Yep.
another 0.5, right?
Right.
Oh, so you have discovered so that this is going to be equal to that. That's my x plus 1 in the next generation. And then is anything going to change ever?
No.
No, that's going to be 0.5. That'll be 0.5, and this will go on forever. Yeah, that's a good point. Okay, so that's what happens when we try R equals 2, nothing special happens. And it turns out that if you pick any number here besides 0 or 1, you're going to get to 0.5 and then you'll stay there forever. That will be a nice stable equilibrium. And this is kind of what we think, like this is our equilibrium economy. This is our equilibrium population. This is our equilibrium weight. You eat food, you burn calories, you stay the same weight every day forever. But if we crank this up to 3.7, things change a little bit. So let's go back and try this again. And let me ask this, does anybody besides Professor Marxhausen want to do the next round of calculations? I'm sure he'd be willing to share. I'm also sure he'd be willing to keep going.
I could do it.
All right,
Yeah,
I just heard, was that Noah?
Yeah, no,
yes,
the
sir.
student Noah is participating, yes.
Okay, thank you. Are you willing to yield the floor, Professor Marxhausen?
Yield.
Okay, Noah, you're up. So let's do,
Okay.
where do you want to start, Noah? Do you want to start at 0.5 or do you want to start somewhere?
Let's go 0.33.
Okay, 0.33. All right, what is 1 minus 0.33?
0.66 or 0.67.
0.67. Yeah, there's rounding there. Okay, and then what is 3.7 times 0.33 times 0.67?
3.7. Well, I'm sorry, what was that? 3.7 times.
Yeah, so it's R times xn times 1 minus xn. So it's going to be this R times this 0.33 times this 0.67.
So 0.37 times 0.33, 1 minus 0.33.
Yeah, exactly. Which is what we already calculated. That's the 0.67.
0.81.
So 0.81. Aha, that's interesting. So 0.81. What's 1 minus 0.81?
That would be 0.18.
1.9?
Yeah, 1.19.
Yeah, well, I guess there could be some rounding in there. That's possible. But let's do this again. So what's 3.7 times 0.81 times 0.19.
0.56, 0.57.
0.56. Okay, so here's my 0.56. And then let's do one more round and then we'll automate it. What's 1 minus 0.56?
0.43.
0.4. There's rounding there again. Can we round it off to 0.44?
Yeah. 0.44.
Okay, and then what's 3.7 times 0.56 times 0.44?
3.7 times 0.44 times 0.56.
Correct.
0.911.
0.91?
Yeah.
Okay. This is interesting. It's bouncing around. It's not settling down at all. Okay, so I'll tell you what I'm going to do here is I'm going to say that is equal to this cell. This is going to be equal to 1 minus the 0.91. I'm just going to automate this. And then this is going to be equal to R with dollar signs to make it a fixed reference times X times 1 minus X, which is C17. That's 0.3. And then I'm going to take this whole thing and I'm going to drag it down a step. Then it goes to 0.78. Then it goes to 0.63. If I drag this down, am I hitting any kind of equilibrium? Noah or anybody else who wants to speak up? Like, am I getting one answer that keeps coming back? Like when Dr. Marxhausen did it, it was always the same. Noah, you want to field that question for us?
Sure. Yeah, you're definitely not hitting an equilibrium.
Yeah, we're not hitting any kind of equilibrium here. In fact, look at this. This was a 0.91, and then it was a 0.3 and a 0.78. Here's a 0.91, but the next one's a 0.29 and a 0.77. Not quite the same. Now, let me ask you this. Was there any random number anywhere in this process? Again, that could be Noah, Professor Marxhausen, or anybody else who wants to chime in.
Then was random, I guess.
Say that again, Halston.
Then was random because it was just picked by Noah.
I guess the first input was random. Yeah, that's true. Right, but once we did that, we didn't go to a random table or use a random number generator. We're getting random looking numbers, even though everything here is completely deterministic. And this is the key thing that got me going as an undergrad. It gave me this idea that, hey, maybe some of the random stuff in the world is not random. Maybe it's the result of something that we don't yet understand. And I thought that gave me hope. It gave me hope that maybe things make sense in the world after all. So I'm getting ready to switch back to the other one. I'm going to notice there's a chat here. Okay, right on. That was Noah. I'm going to stop sharing here, and then I'm going to go back to my other PowerPoint slide. All right. So we just did what we said here. And let me show some results. Here's an example of R equals 2, and a starting point is 0.18. In that case, it's going to go up to 0.5, and then it just stays there. There's no chaos when R equals 2. If we change the initial condition, oh, sorry, there it is, 0.5. If we change the initial condition to 0.19, we get exactly the same thing. This is not chaos because a small change in the initial doesn't give us a big change. In fact, it gives us no change at all. We try to engineer things to be this way so that if a person's driving down the road and they're slightly out of their lane, they can rapidly recover and get back in their lane. That's good design most of the time. Now, let's do the same thing, but with R of 3.7. Here, I chose a starting point of 0.18. It's the same as what we had before. But what we're seeing here is this is the numbers that we're bouncing around. And this is another example of what Noah calculated. In fact, Noah, if you had picked out 0.18 instead of 0.33, you would get these exact numbers in this exact order. it is totally reproducible. There's no randomness in it. It just looks random. All right, and then here's the key idea called sensitive dependence on initial conditions. If we change that first spot to 0.19, it starts off pretty similar, but pretty soon the blue line deviates from the red line. And after a while, there's no way to tell where I started. So this small change in the input gave us a big change in the output. And that is interesting. And there's many applications of this in science and engineering. One of them is that this gives us a way to think about fluid mixing. Mixing is when you have two particles that start off close to each other, and then they end up randomly dispersed through the fluid. If you can engineer a flow that has sensitive dependence on initial conditions, you can improve mixing processes. And that's really important because mixing is the first step that leads to reactions. Reactions are the thing that cleans up the contaminated groundwater. But that's not the only thing that we do with reactions. That's just my particular focus. All right, so fast forward. 11 years later, it's 2005, 2006. It's my first year as a professor here at CU Denver. Here I am in Denver. Here's my commute to work, folks. I live in Park Hill and I ride my bike past this boathouse pretty much every day. It's an honor and a privilege to live here. And the work that I do is mostly under the category of groundwater contamination and remediation. In particular, my group focuses on the fundamentals of fluid mechanics that apply to making fluid flow to improve cleanup of contaminated sites. So this is the cover from a special issue of the journal Water that I co-edited with Timothy Scheibe from Pacific Northwest National Lab. All right, so let's talk a little bit about groundwater. Groundwater is the largest reservoir of fresh liquid water in the world. Most of the water is in the sea, and most of the fresh water is frozen in Antarctica or up in the ice cap. But if you forget about the ice and you forget about the salt water, what you're left with is mostly groundwater. 99% of the fresh liquid water in the world is under the ground. And if you start on the soil and you dig down deep enough, basically anywhere, you're going to hit saturated soil. We call that place the water table. And then it interacts with streams. In this case, there's higher head in the water table than in the stream. So the water is going to go from high head in the water table to lower head in the stream. Sometimes it's the opposite, where the stream is higher than the surrounding water table, and then the stream will be recharging the groundwater. So it's a huge deal anywhere in the world, particularly here in the arid West, where we rely on groundwater to provide a lot of drinking water and a lot of irrigation. And generally speaking, groundwater is pretty fresh compared to surface water because it flows through the tiny spaces in the grains of sand and soil that act as a filter. But there's a lot of things that can contaminate groundwater, so that gets us into the world of remediation. So here's a few examples. So you could have a landfill that leaks. You could have a septic tank that leaks down into the groundwater. You can have fertilizer, you can have pesticides, you can have high-level nuclear waste repositories. In fact, you name it, pretty much any human activity is eventually going to find a signature in the groundwater. And like the sponge next to your sink at home, once this thing gets contaminated, it's kind of hard to clean it out. It's easier to keep the sponge clean. If everybody squeezes it out and lets it dry, it'll stay pretty good for a pretty long time. But once it gets to be really nasty and contaminated, you pretty much have to blame your roommate and then just go buy another sponge. There's no way to clean it up easily. Groundwater's like that too. So if the only thing you remember from my seminar is spend the money now to prevent the spill, that will be the fastest, cheapest way to go. All right, so let's dig in a little more to groundwater remediation. It's a multi-billion-dollar industry here in the United States and around the world. There's some fundamental problems with this. One of them is clogging. The permeability depends on the colloids, like clays. And I've had students working on this problem ever since I started here. That's a little beyond the scope of where we're going here, but permeability is a huge, huge deal. The other thing is plume spreading. So let's say here's a contaminated chunk of groundwater that's underneath an industrial facility. So I'm going to inject some treatment solution. The idea here is I want this treatment solution to react with the surrounding contaminated groundwater. But it's tricky because normally you'll have your cup of coffee, you pour in your milk, and then you mix it up with a spoon. The turbulence is going to drive really efficient mixing. The problem is in groundwater, all the flow is inside porous media, so we essentially never have turbulence. The one thing we rely on to get mixing in fluids is gone. So how do we get this thing to mix in a laminar flow where we have no turbulent eddy structures? And the answer comes to us from our friends in physics who have looked at chaotic advection. If you can have a chaotic flow, you'll get sensitive dependence on initial conditions, and those two particles that started off nearby are going to deviate and go far apart. Porous media, laminar flow, no turbulence. How can we make the plume space filling? And to help you visualize that, here's a picture of Pablo Picasso. You might remember this series from Life magazine, but what he's doing here is taking a light or a flashlight on a time-lapse photography, and then he's moving it around quickly to draw the shape of, I think this one is meant to be a torus, but it's extremely abstract art. What we're trying to do here is we're trying to take this idea, how can we get this, instead of a circular blob, how can we make it fill the space better? And the way we do that is with something called stretching and folding. All right, so this brings us to example number 2. All right, I'm going to stop sharing again. And I'm looking at my door and I'm not seeing anybody. So I guess I'll go ahead and do the demonstration myself. But what I want to get across with this is that in a totally laminar flow with no turbulence, really slow, really sticky stuff, it is still possible to get mixing. All right, stand by. I'm going to need to move some gear. All right, I borrowed this garbage can from the hallway outside my office. All right, that's about good. And then I borrowed this cutting board from my kitchen at home. And then the last time I took my daughter buying birthday gifts for friends, I bought 2 colors. This is yellow Play-Doh, and this is pink Play-Doh. Hey, folks, this is serious NSF-sponsored engineering research, but it doesn't say anywhere that you can't use Play-Doh to get your point across. All right, so I'm going to take the yellow, and then I'm going to take the pink, and I'm going to smash them both into pancakes. So here's a pancake of yellow. All right, could somebody raise their hand if they can see the yellow pancake? All right.
We can.
All right, we're good. All right, and then here's the pink one. So here's my pink pancake. Here's my yellow pancake. All right. So remembering back in elementary school, if you've got yellow and red and you mix them, what color do we get, folks? Remember primary colors? I know it's not red, it's pink, but we're taking what we can get.
Orange.
Orange, yes, that's correct. You get full points for participation. All right, so what I'm going to do is I'm going to stack these 2 on top of each other. All right, now, is there anything here that reminds you of like the turbulence in a coffee cup? Or is this like, this is really slow? Like I got pink sitting on top of yellow. So what I'm going to do is I'm going to squish this. And then I'm going to fold it in half, stretching and folding. Okay, so now basically I have a pink taco on the outside with yellow on the inside, right? And I'm going to squish it again. And it turns out there's a mathematical theory of this. This is called the Baker's transformation. This is a standard thing that people analyze in chaos theory. We're just doing it with Play-Doh. I'm smashing it down again, and then I'm going to fold it in half again. So now I've got layers, right? I've got pink on the outside, then yellow, and there's more pink on the inside. So I'm going to push this again. By the way, does anybody ever make bread? Has anyone made bread? This is literally how you blend dough. You like take the dough and then you flatten it out and then you roll it over. And you keep doing that until you have a nice homogeneous mixture of the two flavors. By the way, look, I'm starting to get a strip of orange here. Can you see that? Then I'm going to fold this over again. By the way, there's a really pleasant smell here in my office. It smells like Play-Doh. It's giving me nostalgic, happy memories of being a preschooler. It's easier to see this when we're doing it in a room. Hey, can you see how that's starting to get orange? Totally zero, absolutely zero turbulence here. But we're doing this in a way that eventually every piece of yellow gets to be pretty close to a piece of red, or in this case, pink. And if we do this enough times, we can get these two things to mix. Yeah, almost there. All right, I'm going to call that good. That is basically light orange right now. If I folded it over a few more times, the color would get to be more homogeneous. But what you can see is I started off with two totally different fluids, yellow and pink. And after folding and stretching a bunch of times, you end up with something that's pretty well blended, even though there's absolutely no turbulence involved. That is the insight that got us going on this branch of research. All right, now hang on a sec. Remember in preschool, you got to put away your Play-Doh because otherwise it's going to dry out. And even though the color may be different, this might be still fun for some kids somewhere. So let me put this away now. By the way, that's also good professional practice for any of you doing research in labs. The cleanup is part of the work. You know, you need to leave your bench in a nice clean condition just the way you found it. All right, now I'm going to bring this back and let kids play at home. Okay, I'm going to go back, share the screen one more time. Here's my slideshow. Alrighty, could somebody please give me a thumbs up if they can see my slideshow?
We can, yes.
You got it. Okay, thank you. All right, so this is exactly what we did. Here's how we tried to apply that in groundwater. So we started off with an analytical model. This was something I learned from Professor Fred Rutz, who's retired now, but he said design happens on a pad of paper. Take out a pad and just draw stuff on it. That's where the ideas come from. He's a structural engineer, but it turns out that worked here too. Because I asked myself, how can I inject fluid into one well, 2 wells, 3 wells, 4 wells, so that this blob of stuff that I injected is going to stretch and fold and fill the space. So I'm assuming an ideal 2-dimensional aquifers, confined, homogeneous, isotropic, and infinite in extent. And I'm assuming transport with no dispersion, reaction, or absorption. So this is in the supporting information to our first paper. So by injecting sequentially and extracting sequentially, I fold it over and then I repeat. So I'm stretching and now I'm folding. And then I'm going to repeat it again. I'm going to stretch and then I'm going to fold. And I'm going to keep doing this and it's going to start to fill the space. All right, I'm going to stop there because this gives us enough information. So this thing that started off as a circle has now stretched. So it has the same area. The area of the shape never changed, but it has a much larger circumference than it had before, which means there's a lot more opportunity for the contaminated groundwater to interface with this treatment solution that we just injected. And this was kind of the essence of our first paper. We've now had a stack of papers that have come out related to this over the years. Let's go to the next one. Let's analyze this just a little bit. When you analyze the flow, there's what we call periodic points. There's a diamond shape, a square, a triangle, and a circle. And this is a point to which the flow returns every time you go through the cycle. Once you identify those periodic points, then we can identify what's called a stable manifold. That is a place where on subsequent iterations, the particle gets closer and closer to the manifold. And then we have an unstable manifold where the particles are moving farther and farther away. And this gets back to that cartoon I showed earlier in the seminar. If I've got two particles on either side, one of them is going to go up and one of them is going to go down. And so the presence of these periodic points with unstable manifolds leads to the generation of chaos. So we were able to go through and show mathematically that what we have here contains chaos in the same way that the logistic map contained chaos earlier in the seminar. Not everything I'm going to show has been shown to contain chaos. Sometimes we're just going for the concept of stretching and folding. And it turns out that stretching and folding may be the really essential thing. All right, I'm looking at the clock here. I've got about 5 more minutes, so I'm going to step it up just a little. Here's the metaphor with the periodic point and the ridge in skiing. So we've done some really cool experiments. Here's the blob that's been moved. Remember the shape? The way we do this is we build this 2-dimensional apparatus. We inject an actual blob, and then we've got a laser that reflects into the dye. Then we choose dye that will absorb the light at one wavelength and emit it at a different wavelength. By putting a filter on a camera, we can see the particles in the blob. The way we do this is using refractive-index-matched porous media. You might remember from back in physics 2 that glass has an index of refraction, and if it's flat on both sides, the light will go straight through. If it's curved, the light will change direction. That's why we have glasses. That is the essence of glasses and contact lenses. In theory, it's very simple to find a granular media and a fluid that have exactly the same index of refraction. And then if they do, the fluid the particles disappear in the fluid. Practically, it's a lot harder than it sounds. If you're going to do refractive index matching, give yourself some time to optimize. Don't assume it's going to work on the first try. That's what I've learned after a couple of experimental campaigns. Here's another detail of the experiment. We got an injection well in the middle and then the 4 wells surrounding, and it's quasi 2-dimensional. And then here's some results. So here's an idea where we start off by injecting, and then we pull the fluid out to the left, and then we pull it out to the right, while at the same time injecting in the middle. So we've stretched it around a fulcrum, essentially. We've got a hydraulic fulcrum here. And then we repeat that process a couple of times in order to take an initially circular blob and to spread it out into something that occupies a lot more space. In contrast to the simulations I showed before, this has a lot of dispersion. That dispersion is good because that's exactly where the mixing comes from. And the experiments we ran in replicate 1 and replicate 2 are extremely similar. And we were also able to simulate everything numerically, and the simulations and experiments were a very good match. Working in porous media, it's hard to get this level of reproducibility. So I'm extremely proud of our co-advised doctoral students, Eric Roth and Lauren Sather, who pulled it together and got this done. This also got us thinking about some really cool theory. Essentially, you want the fluid velocity to be perpendicular to the interface because you get better mixing when things are perpendicular than, in this case, where the velocity is parallel to the interface. I'm skipping through this a little bit, but here's a way that we've engineered this to work. These are the flow lines, and then behind it are the plumes. So there's an area here where basically the streamlines are perpendicular to the plume, and we were able to show that optimizes simulated mixing. Here's an experiment, and here's a numerical analysis showing that. So in the end, is chaos the answer? Have I just discovered the one thing that's going to answer all of our problems in engineering? And the answer is no. It gave us a way to start thinking about the hydraulics of remediation differently. But the bottom line is always public health, safety, and welfare. And so here's an example where chaos is not the answer. If you have a sorbing contaminant shown in red, and you want to treat it with a treatment solution shown in black, your best bet is to inject the black stuff right in the middle, because the red stuff will be sticking to the soil. And then you want to gently wash it with the black particles to decontaminate. You don't want to engage any kind of chaotic flow if you have sorbing contaminants. The contaminants we showed before, those were always based on the assumption of aqueous phase. They're just floating. But what we've learned is that by using hydraulics, we can improve mixing processes, whether it's chaos or not. So the next step we're looking at is working with industrial partners to try these ideas in an actual groundwater remediation field site. All right, some conclusions. Chaos is cool, chaotic advection works, and we've learned a lot. Here's that theory picture I showed before. But chaos is not really the point. It's not enough to be cool, it also has to be useful. Here in the world of engineering, we care about solving problems in the real world. The bottom line is always public health, safety, and welfare. So the approach we've developed under the heading of engineered injection and extraction, it's an approach to make groundwater remediation work better by deliberately engineering how the flows go. And the next step is field testing. So I'm going to wrap up there and say thank you to everyone for your kind attention. I know we've got a few minutes. If you don't have to rush off to class, I'd be delighted to answer any questions.
Yeah, thank you, David, so much. It was very interesting. And yeah, now I encourage the students to ask questions, whether it is on the chat or verbally saying the questions. So go ahead, guys.
Hi, Professor David. I have some question. Actually, some idea like which traditionally used in fluid mechanics, where to mix fluids. By the way, is that possible for me to share my screen?
Yes, let me give you co-host rights here. Just give me a second. Okay, so where do I go now? Participants, and I need to find you now. Okay, make it a co-host. Yes, now you can.
Like a mixing from a traditional fluid mechanics kind of fluid dynamics kind of point of view or engineering point of view. I think of two devices. First is like a very typical fluid mixer, which is anyone can see my screen?
Yes.
I can see your palette, but I haven't seen anything drawn yet.
Okay, yeah, sure, yeah. I just like think of two devices, so or two kind of a way to mix fluids. One way is to create circulation, which is like a traditional way to making mixing fluids. For example, if we have a kind of a circular shape of container, and usually we have traditionally we should have like pellets or something inside to rotate and create circulation. But
Right.
the other way to do like in fluid mechanics, we can do is we have a inlet and outlet at the tangential direction of the fluids. Like we can have inlets, we have going this way, we can have outlets going this way. So this kind of fluids motion can create a circulation, which is good for making like fluids to mix fluids. So is that possible to achieve this kind of motion by using, because when you're talking about your way to fold the blob, it seems that you have a way to inject and extract fluids from the.
Right.
Yeah. So
Yeah.
I was thinking,
So,
is this?
Yuchen, yeah, this is a very insightful question, and you're absolutely right. I think about this in sort of two categories. One category is turbulent mixing. So if you can engineer anything that imposes turbulence in a way that's as homogeneous as possible, you can get the fluids to mix. For instance, inside internal combustion engines, you want the gas and the air to mix in a way that's nice and uniform so that when you ignite it, it burns in a uniform way too. In the world of laminar flow, we don't have turbulence, but sometimes we can still impose rotation. And that's the typical way, like if you have paddles inside a vessel, those actually have been shown to induce chaotic advections as well. The unique challenge we have in groundwater is that you don't have anything like a paddle. You can't stick a paddle in and twist it because the fluid is inside a matrix of porous media. So you don't have a way to impose rotation. Sometimes we get rotation incidentally when you go from one permeability to another permeability, but except for that kind of technical detail, the flow in porous media is basically irrotational. So one of the major contributions in that first 2012 paper was to show that you can generate a chaotic flow that is also irrotational. And that got us around one of these technical challenges. But yeah, you're absolutely right. Imposing circulation is a classical way to go, whether it's turbulent or laminar.
Okay, and actually another idea I was thinking of basically just since you mentioned internal combustion engine, I was thinking about like a carburetor, which is like a traditional way to mix to have a good like a fuel air mixture. So basically a carburetor like the very easy way, the very simple I guess a sketch of carburetor is that we can have a jet of fuel and heating on a plate to
Right.
Yeah. So in this case, sorry, in the point from mixing the blob, this point of view, is it possible to have like a little bit stronger flow and a little bit like less strong flow? You use this way to create turbulence to have like two laminar flow in opposite direction, and one is slightly stronger than the other. And then is that possible to use this kind of way? This kind of method?
Yeah. So right, exactly. So a carburetor is the classical way to blend the gasoline with the air before it goes into a cylinder in a car. And your question is, can you engineer a flow so that you have one flow coming one way and another flow coming the other way with sufficient momentum that when they hit, you generate some turbulence?
Yes.
In principle, it's possible to generate turbulence inside porous media, including soils, but practically it's very, very difficult. And it comes down to a concept from fluid mechanics called a Reynolds number.
Yeah.
Are you familiar with this concept?
Yeah.
Yeah, basically you've got density on top and viscosity on the bottom and velocity on top. So basically it's momentum on top. And then there's also a length scale on top. And in groundwater, it's moving very slowly. Typically, our flows are on the order of 1 meter per day. That's incredibly slow flow. So there's not a lot of momentum. And the pore sizes are very small. We're looking at 0.1 millimeters, maybe 1 millimeter, but that's kind of a superhighway in groundwater. If you had a gap of 1 millimeter, that's an incredibly big pipe. In the world of pipe networks, that's incredibly small. So because it's very small and very slow, the water acts like honey, which is one of the brilliant things about fluid mechanics and the idea of dimensionless variables is everyone's familiar with honey, like it will pour, but it takes forever. It takes so long to pour the honey. In the world of groundwater, you can think about the water acting like honey, rather than acting like the white water going down Cherry Creek outside my office on a flooding day. We're just dealing with sticky fluid because the viscosity is so much more important than the inertia in that case. So no, I'm not aware of a way that you can generate turbulent mixing inside a porous media application. But if you want to talk about that more offline, I'd be interested because I like how you're thinking. This is the good way to go. And it speaks to an idea that if we start with fundamentals, sometimes those fundamentals will lead us to better designs. And I feel like that's where we come in as engineering researchers at universities is let's think about the fundamental engineering science, and then let's think about the application, and let's try to forge that connection in a place where it might work or it might not. We don't know in advance. That's why we call it research.
And one last question, because I'm not very familiar with like water, underground water stuff. But I was thinking, like, is there a way to have a, for example, if a point, if we have a contamination in certain area, is that possible to, for example, if we have a contamination in certain area here, and is that possible to like drill a well somewhere near it, and we can like force a pumping amount of water into the underground to try to like manually create some kind of turbulence, or to do this kind of
Yes. So in general, it's hard to generate turbulence, but there are other approaches to cleaning up contaminated groundwater that are based on putting a well near the contamination and then operating the well so that you extract all of the contaminated water along with a bunch of uncontaminated water. You take that stuff and then you treat it in an engineered process outside the ground. That's called pump and treat. And that is probably still the basic way to do this. However, there's a lot of known problems with pump and treat, which is why a lot of folks over the last 30 years have worked on what we call in situ groundwater remediation, in situ being a Latin phrase meaning in place. So the work we've done is really focused on in situ remediation rather than pump and treat. I saw there was one question in the chat, but I also noticed that it's high noon. So I will pass it back to the organizer, Professor Mancia David.
Yeah, so I don't see any questions on the chat. I mean, we could try to answer one more question in case there was one.
Professor Tom did have a question, actually. He said, "Is the
I don't see it on the chat. Sorry, yeah.
I think he sent it to me directly, so that's
Oh,
fine.
I see.
Yeah. So he said, "Is the temperature accounted for in this type of chaotic flow mixing?"
Is temperature accounted for in this kind of mixing? So far, we've always assumed things are isothermal in this line of research. However, we've also, separately within my group, we've done some studies on what happens if you inject hot fluid into cold fluid. How does that trigger additional mixing? Those are other results that we're currently preparing for publication. And the short answer is yes, it seems to help a little. It's certainly something that you could do in addition to what we're doing here. And it comes down to changing, when we change the temperature, it changes the viscosity. And when you have a viscosity difference, that gives you some other fluid mechanics that we call viscous fingering. And that's a whole nother talk, but it's an interesting line of inquiry.
Hi. So, well, David, thank you so much. I think we're, ready to wrap up in here. So it was very interesting. I appreciate it very much, and I hope that the students did too. So before we go, just for the students, you guys can see my screen, right? With the schedule of seminars, yeah. So because of spring break, we are having another seminar next week, okay? So on March 14th, we will have Dr. Chelsea Maggie giving us a seminar. And then we won't have any other seminar until April 4th. That's because of the spring break week, that is in between in there. So for the students, I look forward to seeing you guys on Tuesday, this upcoming Tuesday, March 14th at 11. And other than that, again, thank you again, David. And yeah, so we will be in touch. Thanks so much, everyone.
Thank you
Have
for
a
the
good day.
invitation. Thanks, everybody, for your attention.
Thank you. Bye-bye.